Hello, YouTube. Thank you for tuning in to the 2019 June Fusion Shark Tank. This is a regular monthly call that we hope to continue, where fusion startups pitch their technology, their commercialization approach, and their team to potential investors. Tonight we have two great startup teams. The first one is Princeton Satellite Systems from Princeton, New Jersey. And the second one is CT Fusion from Seattle, Washington. The presenters are Dr. Charles Swanson for PSS and Dr. Derek Sutherland for CT Fusion.
Woohoo! Cool.
Okay, so here we have it. The Princeton field reverse configuration. Small, clean, dihelium-3 fusion reactor. This is the team. First, we have Princeton Satellite Systems, and we have a doing business name as Princeton Fusion Systems. And that's Stephanie Thomas, who's also on this call, the vice president. Mike Palushek is president, and me. And then at PPPL, we have a subcontract with them to run their PFRC experiment, and the PI there is Dr. Sam Cohen. Here's my outline here. I'll describe the team. I'll give the value proposition, the market for this system. It's a restricted high value market. And then I'll give the flip side, the other side of that coin. Why are we not going after a mass market? Well, it's because of the limitations in helium-3. I'll show a little animation. Actually, in testing, I wasn't able to get the sound to work, so I think I'll have to skip that. I'll paste the link into the chat so you can do it on your own time. I'll describe an overview of the technology. I'll hit the key physics points. I'll describe where the experiment is currently, and I'll give a path forward to fusion and revenue. After all, this is a Shark Tank. So Princeton Fusion Systems, it's a doing business name as for Princeton Satellite Systems, which is mostly a advanced technology for spacecraft company, which was formed almost, it's 25 years ago, more than that. So the PFRC is sort of a departure for that. It's a fun project that we are contracting with Princeton Plasma Physics Lab to develop. So this is what is the market? You'll notice that I'm not saying the market that everyone's saying, which is baseload power, which is saving the planet and powering the world. Instead, we're describing a relatively small number of very small, clean, practically aneutronic fusion reactors. And for civilian power, basically anywhere where the majority of the electricity is the cost of trucking in diesel, or anywhere where you need power fast and reliably. For example, remote villages or research stations, things that have been hit by disasters. Then another high value application is NASA and the Department of Defense in space, powering expeditions and experiments, and even deflecting long period comets. It's one of the few pieces of technologies that I know of that could actually get to a long period comet in time to deflect it. Moving over to the Department of Defense Terrestrial, we have all of these, diesel convoys are a big logistical problem currently, and this would replace a truck full of diesel every week to a suitcase of helium-3 every 30 years. And so there's a serious logistical advantages to using a small, clean helium-3 burning reactor. Of course, the flip side to this very restricted high-value market is that we can't go any farther. Oh, hold on, I'm sorry. There we go. Because in order to be so clean and small, we must burn helium-3. And helium-3 is a scarce, non-renewable resource, and we only have so much of it. Helium-3 is currently produced as a byproduct of the nuclear weapons stewardship programs in the major nuclear weapon states, as tritium decays into helium-3 naturally. And so, given the amount of helium-3 that's being produced by these programs, we can say that in steady state, the amount of helium-3 that we have in production right now can give us 100 megawatts continuously. So if you only need it in bursts, it can be more than that. If you only need a few of them, you can stockpile and save them for big important things like asteroid deflection. And then towards the bottom of this page, we've got things like, if you really wanted to do something like power the world, in the long time horizon of this is you really could mine the various celestial bodies that actually get helium-3 directly from the sun's fusion. So mining the moon, mining the gas giants, the ice giants are actually a better bet because it's easier to get to their surface. So here is the part that I'll sadly have to skip, but I can copy paste these. Can you all see my mouse? Or am I just referring to these?
Yeah, I can see the mouse. You're
Great.
over the YouTube link.
Correct. Yes. So this
Yeah.
is the one that I think you'd be most interested in because it's an overview of our technology for a lay audience. But I'll have to skip it at this point because I couldn't get the sound to work over Zoom. All right, so the technology. Why do we think we can do this? Well, the real key point here is this, our simultaneous current drive and heating method. It's odd parity rotating magnetic field. You might call us a third generation Rotamac for that reason. It's a set of antennae that sits on the outside of the plasma externally, and this one set of antennae both drives currents, forming the FRC, and heats the plasma. And it's because of this and because of the helium-3 that we can make it 3 words: simple, small, and clean. And I'll go into each one of those in detail. And as a result, I'll go into each one of these in detail. To the right there, I'll go into this. So first thing is unique heating. Rotamacs in general, you have historically used what has later been termed even parity rotating magnetic field, where you have picture frame antennae around the plasma column, and you set up the phase of the RF signal so that the magnetic field induced by the antenna rotates. And this drags electrons along, but also opens up the confining magnetic field so that particles have a chance to escape. Sam Cohen's big enabling technology was the idea that instead of having one picture frame, there should be 2 picture frames and the sign of the current flips across the midplane. This means that any deviation of the confining magnetic field exactly cancels and the field can remain closed. As a fun added bonus, it turns out that if you do a couple right-hand rules in your head, you can see that the inductive electric field is maximum on the midplane. So this actually makes it more efficient at heating, and it can heat ions. That's what we're supposed to be proving out right now. Next word is simple. Instead of building demountable toroidal coils and all of these horrible blankets and things, it's a simple linear array of coils. The entire thing can be pulled apart on rails or added. It's difficult to overstate how important this feature is. The engineering is much simplified. It's also very small. On the left, you see an engineering model of ITER with a person down at the bottom of a scale. On the right, you see on the same scale how we imagine an eventual PFRC power-producing reactor to look. It's much smaller. Instead of making gigawatts, it makes a few megawatts. Instead of 60 meters tall, it's 2 meters in diameter. And because of that, and I'll get to this a little more later, a faster iteration cycle actually means we can lop off literally billions of dollars from the development program. Now, the last thing I said was clean. And as you may know, when deuterium reacts with helium-3, it produces no neutrons. But when deuterium reacts with deuterium, as it always will in a d-helium-3 machine, it produces half the time a neutron and half the time a triton, which produces an even worse neutron. And so we have a suite of technologies here which can take the neutron power fraction from more than, around 80% from a DT burning tokamak down to less than 0.05%, which is a big deal. It heavily simplifies the engineering. It heavily simplifies the construction of the first wall. It means you don't have to license for tritium, for example. You don't need to do all the neutronic breeding stuff. Here are those technologies I described. Every step on the right here goes from a DT tokamak to a PFRC, and we've just isolated all the various pieces that make it aneutronic. So in the first one, we go from a tokamak configuration to an FRC, which actually makes things worse because you're removing that center stack, so the flux goes up. Next thing, instead of burning DT, you burn d-helium-3. Which brings the neutron flux down, but not as much as you'd like because you still have the DD producing a neutron and a triton. Next one is rather than going from meters of radius, you go to tens of centimeters of radius. Because of surface to volume scaling, that actually decreases the flux by a lot. The real big one is number 4 here, which I'll describe in the next slide. We have a way that we are fairly confident with numerical simulations and analytic reasoning, we can promptly exhaust the tritium that's produced before it fuses, which is essential to the entire concept. I'll describe it in a moment. And then you can do a couple of fun things like change the helium-3 ratio so that there's more helium-3 than deuterium. And we think we can also heat selectively the helium-3 via our rotating magnetic field and produce a helium-3 population that's hotter than a deuterium population. So that gets it all the way from 3 megawatts per meter squared to almost just a kilowatt per meter squared. This is how we can get it, how we think we can get it so clean, which is essential for our value proposition. So here's that tritium ash removal. The core is hot and it's dense, but outside the core is this open field line region that we're free to densify with a colder plasma. And the plasma physicists of you will know that the collisionality decreases as 1 over temperature to the 3/2, which means that when these tritium nuclei, when these tritium ions escape the core and go into this, we used to call it a scrape-off layer from comparison with tokamaks. Now we're trying to think of a better name, for example, exhaust shell. That's what I'll call it here. When it goes into this densified, colder exhaust shell, it slows down so much more than the core that all of the tritons are exhausted in this shell, and before they're all exhausted in this shell, the vast majority of them before they fuse. On the left, you can see a schematic representation. It starts off with these big spaced betatron orbits, which is how you can tell it's a high energy particle. Then as it loses energy, it goes slowly into a figure 8 and then a cyclotron orbit and is finally exhausted outside the core. That's an exaggeration. It actually happens on a longer time scale, but still a much shorter time scale than the tritium fuses. All right, and we calculate that it's so ultra low radiation that the amount of shielding you need between the core and the magnets is a few dozen centimeters. We like to say 20 centimeters. And the shielding you need between the core and people operating it, and I will point out that this person right here is actually me, is just a meter of shielding. It's concrete with steel inside, and that's how close you could be to an PFRC scaled power reactor. You wouldn't have to have this bioshield. You wouldn't have to have all of these decimeter warnings all over the place. It's really much safer than how people imagine DT tokamaks to work. All right, so now, why do we think this will work? We have a set of results, both numerical, analytic, and experimental, that gives us confidence that this will work. So we have, when we trace individual particles in the magnetic, electric, and rotating magnetic fields that we expect in the machine, that it shows that these individual particles, so neglecting collective effects for this analysis, it shows that you can drive current and explosively heat both ions and electrons. Moving down one, our first machine demonstrated that electron part, though it operated at too low a power density magnetic field and too high a frequency to heat ions. And so it got a record, you know, it kept the FRC stable for 10 to the 3 alphane times. And now we're operating PFRC4, which I'll describe in detail. We've had a greater power input. We've turned down the RMF frequency, and we've got to a higher magnetic field, and we've gotten better electron results. We have an ARPA-E grant that I'll describe a little later that is funding this machine over the next 18 months. The goal of that is to demonstrate the ion heating. That's something that's predicted from the Hamiltonian code, but has not yet been observed. And so that's the goal of this ARPA-E grant. And finally, down to the bottom there, you see that we have PIC models, which, unlike the Hamiltonian code, do include collective effects that really do show a field reverse configuration forming and current drive and heating from this odd parity rotating magnetic field. Then down in the bottom there, we also, you know MHD modes or crazy high drift waves are going to show up. We've done our homework with respect to how much we expect the FRC to be stable, what its transport rate is supposed to be pegged at according to our current best guess theories, and how far into the plasma the rotating magnetic field is meant to penetrate. Now, hold on a second. There we go. Yes, the current status of the machine, this is a PFRC2 at this point. It has a larger Lexan vacuum vessel and more power. To the right there is an X-ray spectrum indicating that we've gotten much higher powers, so higher temperatures than the PFRC1. We've operated it at a higher power, 50 kilowatts. Our amplifier can actually go to 200 kilowatts. So a lot of our current experiments are just slowly walking up the power to make sure that what we expect to happen is going to happen. And then the real bread and butter right now, the agency that's funding us is a contract under the ARPA-E Open program. And the run cadence has sped up a lot since this happened. We went from running 1 day a week to running 3 days a week. And I got to say, it's a good problem to have, to be so busy in this machine. It's a beautiful, beautiful machine. It's here we go. So programmatic support, who has actually funded us? Well, you can see there that we've been funded by the Department of Energy in large part for 2 precursor experiments in the current experiment. And then this machine, I didn't mention this in detail, but we expect it to scale very well into a fusion rocket with truly transformational capabilities. So there was a NASA NIAC program, who the PI there was Stephanie Thomas, who's on the call. So afterwards, if she's still there, maybe she can answer questions about that. Then we have a NASA STTR to look at a conduction-cooled low-temperature magnetic coil that we're going to be taking possession of next month. And it's going to be a really cool magnetic coil. We're going to be testing the sudden inflation of a high beta plasma in these low-temperature superconductors to make sure that there won't be any problems with startup. And then finally, we have this ARPA-E open that over the next month will demonstrate whether or not this system can, in fact, heat ions as we expect it to. And now here's where I really want to describe how much size infects everything. Every quarter, ITER has this really beautiful shot where they drone over the construction site, and they have these really neat narrations, things like, we're pouring more concrete than the volume of the Great Pyramid, and we have more than half of the world's population represented and stuff. And that's really impressive and cool and necessary, but it's also expensive. Size infects everything. If we had $10 billion on this machine, we literally could not spend it fast enough. We wouldn't be able to. We imagined that if our pot of money were bigger than around $200 million, the research program just wouldn't support that. We expect to do 4 iterations of the machine in the same time that ITER is just going to be turned on. All right, so path to fusion. Right now, we've confirmed the field reversal. We have a very long, stable FRC. I don't think I've mentioned the actual time. 300 milliseconds is the longest time we've held an FRC stable, and it only went unstable because we stopped heating it. Our capacitor bank ran out at that point, and it went away. The next steps are to raise the magnetic field in power and lower the frequency, because that's the regime in which the ion heating is expected to turn on. At the same time, we're doing parallel paths for some of the engineering components, for example, these low temperature conduction-cooled superconducting magnets. And then finally, this machine will heat ions, but not to this sort of collisionless regime, high power density regime that we expect to need for fusion. So that would be another machine that would use the magnets that we're feeling out with this project. It would be higher power. It would be a larger machine. It would be higher magnetic field. You can see it on the lower left-hand corner there. This is our parameter space with the 2 things that just take money to make. A magnetic field takes money to make, and the plasma radius takes money to make. So you can see PFRC 1 and 2 on there, and the next one would be PFRC 3 and 4, which would actually produce measurable fusion. Not break even, but measurable fusion to the point where we'd be confident that nothing nasty is around the corner. And you can see that in a written form right in this table. And here's our business plan for the sharks. I don't know who the sharks are here. Future sharks watching on YouTube. So right now we need to do these final 2 demonstration reactors. When the ARPA-E ends and we have ion heating, this be a very good case for these funding these 2 reactors. And then the first application shouldn't be baseload power, because you're competing with solar, wind, you're competing with fossil fuels. The first application needs to be something where you provide unique capability. So it doesn't matter the cost per kilowatt hour, because it's going to be high, because no one's ever done this before. So the space flight applications are an example, or military. And then remember, we produce enough helium-3 that there can be a real fleet of these reactors, either on standby or going at all times. So the next step down is that step going out into lower and lower value applications, research bases, and forward deployed bases where you don't have to worry that your prototype costs $500 million to create. And then at the bottom there, we have finally the kinds of things that this can do in the civilian sector. With enough helium-3, you could really compete with solar plants. You would start with the remotest places of the world, the Alaskas, the Congos of the world, where it's difficult to get resources in. And you would work yourself out from there as the plants got cheaper, and if you could produce a source of helium-3 as a byproduct of another industry or in a dedicated industry. That's my contact information there. And down at the bottom is the Princeton Plasma Physics Laboratory principal investigator's contact. Now, I think that because I ended early, Matt, would you like to do this, that I can answer questions, or would you like to go directly into Derek's talk?
No, go ahead and take questions. I
Right,
ask questions if nobody else does.
Sure thing. Ready.
Okay, so any major accomplishments in the last 6 months for this project?
None published in a peer-reviewed journal. You'll have to keep your eye out for that. Sorry.
Okay.
We're working on it. We're running 3 times a week. I'm exhausted all the time. Put it that way.
Okay. Are you currently hiring, for example?
So we have a very specific job that we need. We're looking for a plasma physicist who has the same kind of skill set that we need. The current machine has populations that are strongly wall coupled, that are very collisional, and that are very collisionless and high beta. So we are hiring, but it's really difficult to find someone with, and who's willing to relocate to Princeton. That's important. We're definitely looking for someone, but it's tricky to find exactly what we need, it turns out.
Okay. So your current you've got 4 grants, if I remember correctly. ARPA-E Open, you got an STTR, you got the NIAC, and you got one other one.
Yeah, so we have an IMOD one, and the NIAC, it may have ended now. I'm sorry. I'm sort of a little bit muddled on my dates here, but yeah, the 2 real big ones going forward are the STTR and the ARPA-E.
Open. Stephanie Thomas. The NIAC just finished. Yeah, the NIAC finished last month.
Yeah.
Okay. So your value proposition is you want to do $3 million in seed investment. Is that correct or incorrect? Is that $5 million?
Yeah, so that's $5 million there, and that's for the PFRC3 to prove that you can get to a parameter regime which is essentially identical to fusion. You're just not actually reaching that threshold where you're getting a lot of fusion events.
Okay. Is this going to be a superconducting machine?
Yes, it will. Superconducting around 20 centimeter plasma radius. Not much higher power, actually. I think we could probably use the same amplifier even. But yeah, that machine would also be a cool test bed for our antennae, because the antenna that we're using is the first thing that worked. We have ideas for how to improve the efficiency there. Yes is the answer. $5 million for that, and that's what it's supposed to do.
Anyone else?
Yeah. Sorry. I think you've kind of already said this, but your total funding, what has that been? And has none of it's been venture capital, or
That's
has?
correct. None of it has been venture capital.
Okay.
Yeah, it's all been government. The government has been good to us. Also, sorry,
Yeah.
Can you say your name? I don't actually see you.
Peter.
Oh yeah, you're Peter from earlier, from General Fusion.
Yeah.
Okay, right.
So we've got Stephanie, 635,000 from NIAC, ARPA is 1.25 million, and STTR 750,000.
Thank you, Stephanie. I'm very glad you're on the call.
Yeah. Cool. Okay.
So go ahead, Peter.
It's like 3 million-ish. Okay. And how long have you guys been doing this?
Well, the machine has been in operation since the early 2000s, but it's been
Okay.
Sam Cohen and a few graduate students and a part-time technician on a DOE grant. It's really picked up, and our collaboration has started since the sort of mid to early 2010s. So it has been years, yeah.
Okay.
But these things take time.
Cool. Okay, and then a technical question. You said that the stability was 5 times better than MHD prediction.
10 to the 5. Sorry, what I meant by that is
10 to the 5.
Yes.
Yeah, what does that mean? What does
Sure
that mean?
So if you had this FRC, this magnetic configuration, and you apply the MHD model to it, infinitesimal Larmor radii, and there's no beams or anything, everything's at the same temperature, electrons have no mass and all that stuff, you would predict that any FRC anywhere in the world, no matter how lovingly you construct it, is unstable to several modes, the worst of which is the n=1 tilt mode.
Okay.
However, when you do it more carefully with either a kinetic or a two-fluid analysis or a finite Larmor radius analysis, several people have done this different ways. They always get usually the same stability boundary. And furthermore, the number one thing is that the LSX experiment in the 1990s at Los Alamos also proved this experimentally. A very kinetic FRC, where you have a small number of ion thermal gyroradii between the null and the separatrix, is stable. And so we've also demonstrated that by, it's predicted to fall apart to the MHD tilt mode in an alphane time, which for our machine is a few microseconds, and we've held our stable for hundreds of milliseconds. So
Gotcha. So it's just, stable time over predicted stable time.
Yeah, and we can't actually
that's a big factor. Yeah.
It's to the point where, we're confident that it's stable at this point to that mode.
Cool.
All right.
Okay,
So
cool. Thanks.
I can keep going. If you take investors, are you going to be interfering with their government contracts, or we don't know at this point? It would depend, I guess, right?
Well, we're expected to furnish cost share. It would not interfere with government contract.
And an investor would be buying stock or shares in the company?
Right. So the way we imagine doing it is private equity, right? You would get equity in the company.
Okay. The dimensions, I'm sure I saw the picture, but the PFRC2, is it the same size as the machine in Sam Cohen's lab, or is it bigger or different?
So the PFRC2 is the machine in Sam Cohen's lab.
Okay.
We eventually imagine that scaling it to a reactor that's around 4 times larger in linear dimension.
Okay. So for those who don't know, Sam Cohen's lab, the machine is maybe 3 or 4 feet long, and it's probably about 12 to 14 inches wide, bigger.
Yeah, it's 10 inches inner diameter, and it's 88 centimeters. Wow, I just mixed units there. Sorry about that. That's how long it is. Yeah.
And the value with this approach is not necessarily the size. People forget that. It's the stability that they've been able to achieve and the technique that they're using to do it, which is fundamentally different from the way TAE is doing it. Correct?
I mean, don't discount the size. I just made this whole big argument that the size is important.
Okay.
But yes, you're right. The TAE's equilibrium and our equilibrium are very different. They have FRCs are as varied and zoo-like as tokamaks are. For every spherical tokamak and toroidal theta pinch and doubly diverted snowflake, crazy twisted notomac and whatnot. There's different kinds of FRCs also. Their machine is MHD stabilized by their crazy intense high beam ion population, for example. Our machine is stabilized via this finite Larmor radius effect. They're very different machines. They're very different plasmas.
Okay. Go on, Peter.
Yeah. Are you tempted to pitch Bezos and Elon Musk and be like, hey, buy me and I'll get you to Mars faster?
So I used to work for SpaceX, and I can say with intermediate confidence that Elon Musk isn't interested. If you have Bezos's number, shoot it my way.
Okay.
Well, part of doing this,
I'll let you know.
Thank you.
We can get you to a larger network of people. People know people, and maybe somebody on this call or somebody that watches this can get in touch with you.
That sounds good to me. Yes.
Okay, cool. So you would like that. I mean, would you just tell him dollars per megawatt? How would you pitch it for a Mars mission?
Mars? Wait.
Yeah.
I mean, okay. So I would say that in order to get to Mars, you need to get there fast in order to avoid the astronauts dying of radiation.
Would you say 30 days or something? Or
we can't do 30 days. We can do 45 days. We're pretty confident.
45 days.
Yeah, and actually, by stripping out the shielding and making it a throwaway engine, you can get there faster. But Princeton Satellite Systems is an expensive company. We do this for fun, for money. We have put together very mission plans for the kind of crazy awesome things you could do with fusion rockets, specifically our fusion rockets. So we have good numbers for these.
Oh, cool.
So your fusion rockets, are you heating a heavier element
No, so that's a possibility that we've considered and we're not discounting it. But the way that we imagine it working right now and our baseline design has that exhaust shell. Remember the one thing that's absorbing all of the fusion energy just flowing out the back through a magnetic nozzle. And so if you just shot the fusion products out the back, you'd have an amazingly high specific impulse, but an utterly useless level of thrust per power, right? And so the fusion products thermalizing with 10 to the several bulk products gives you that intermediate specific impulse and thrust that ends up being in a very good place for human Mars round trips, or going out to the solar gravitational lens, or going to any of these other plans. So yeah, that's how we imagine it so far. If you want to go to crazy high specific impulses, you can just run it as a power unit and have a different thruster with a high specific impulse do that instead. Or if you want to run it at higher power thrusts, you can again cap it and have it run a separate electric thruster. But with the range of specific impulses and thrust that we're talking about, like 5 to 10 newtons per ton per megawatt, we imagine around a ton per megawatt. And 200 kilometers per second exhaust velocity, for example, that's right where the exhaust shell just naturally sits. So that's how we imagine that currently.
Oh.
Okay, Derek has a question.
Yeah, so for your reactor design point, what type of plasma gain are you shooting for?
Right, so our plasma gain, we're shooting for around 10. However, it is not an ignited machine. You'll notice that instead of thermalizing with the core plasma, our fusion products just leave. So every chunk of power that's heating the plasma, we are planning to put in. It's not going to get power directly from the fusion products. So our recirculating power has to be pretty high. You know, we imagine we can get 40% pretty well just by, well, I'm sorry, around 20% total, because around 40% of the power leaves just as things that heat up the wall. For example, stray particles, microwaves in the form of synchrotron radiation, and Bremsstrahlung in the form of X-rays. They heat up the wall, and you run that through a heat engine that has 40 to 60% efficiency. And then your RF amplifier can actually be like 90% efficiency. It's pretty cool. So the fact that we're not doing it ignited, but we do expect to get fusion gain is not a deal breaker. That's okay for us.
What does your reflected power fraction have to be to hit your design point?
By reflected power fraction, what do you mean? Do you mean directly reflected?
Synchrotron and Bremsstrahlung back then.
Right, okay. So that's a good question. Bremsstrahlung, we're losing. We're not reflecting it back in at all. That's not gonna happen. Cyclotron, in this particular case, it's more like synchrotron, but we operate in this weird position that's overdense. So for a large portion of the plasma, well, the long story short is that we've looked at it a lot, and the design closes in certain cases for a large portion absorbed. Like even if you're absorbing half of it, the design often closes. We think we can get closer to 90% just by coating well, you know what I mean. Yeah. But we are not relying heavily on synchrotron reflection to hit our point. Don't be alarmed about that.
Okay, yeah, I was just thinking from power balance. You're having to maintain a non-isotropic velocity distribution function. I just was curious what the exact gain you're shooting for, but sounds good.
All right.
Okay, if there aren't any other questions, we'll start with the next presentation.
I've got a question. This is Sam Wurzel. And just by way of introduction, I was working on a FRC mission at University of Colorado back in 2016. And then I started a company called Octopart, which was funded by Y Combinator, and we sold that in 2015, and now I'm investing in fusion startups. And I was wondering what kind of instabilities you are anticipating, if any, as you go to higher, as this thing gets bigger, hotter, denser, etc.
So we're definitely going to run into an m=1 instability where the plasma doesn't stay centered, but it's very easy to deal with that using active feedback. You can see papers and posters in which Tri-Alpha has done this, and you can see the centroid of the FRC moving around, and then they turn on their active feedback and it goes centered. We haven't done any of those controls yet, but we imagine that's going to show up. Other MHD modes are likely to show up, analogous to fluting modes. So these ones where the FRC becomes elongated or threefold elongated. From the micro instability standpoint, setting the transport, we expect that the lower hybrid drift instability is probably going to show up. And so we bake that into the design, but when people actually look for this in FRCs that are at the right parameter regime, it saturates at a way lower level. We're not expecting nasty things around the corner. Of course, plasma has a way of surprising you when you're most vulnerable, but those are the ones we're really looking towards in the future.
Thanks.
Okay, anybody else? Okay, all right. I think we're gonna, thank you, Charles. We're gonna let Derek.
Great, thank you.
All right, so our next speaker is Dr. Derek Sutherland, who is the CEO of CT Fusion. So a little bit of history. Tom Jarboe is a professor at University of Washington. He was at Los Alamos for years and then moved over to University of Washington. And they created the Hedesai spheromac. And a spheromac is a loop of plasma that contains itself. Right. Well, it's similar to an FRC, but it's slightly different because there's an extra magnetic field. The loop has a wobble. Okay, it's inherent in the design. So Jarboe's innovation was to impose. I'm getting this all wrong. Jarboe's innovation was to impose a wobble and cause the spinning effect, and it turns out to be a triple win for the design. It eliminated the instability. It was an innovative way to heat the plasma, and it stabilized the spheromac. I'm going to get this all wrong. Anyway, that paper was published in 2011, and it led to a design called the Dynamac, which CT Fusion has commercialized. So without further ado, Dr. Derek Sutherland.
Thank you for the introduction. I mean, that was pretty good. So my job is done here. You already did it for me. Okay, so as Matt mentioned, so I'm Derek Sutherland. I'm the co-founder and CEO of CT Fusion. We are a spin-out company from the University of Washington, and we licensed IP that was generated at University of Washington, and we're commercializing it at this private company. And so today I'm going to give you a quick overview of our technology that we're developing, and also just where the company's at right now. If I can advance this slide. Okay. So as starting with an outline, so I'm going to give an overview of the sustained spheromac research historically and where it's at today. And then talk about our plasma current drive technology concept, which is really the main value proposition and the main source of breakthrough for this type of fusion, which I think is pretty unique. And then we're going to talk about a vision for our fusion energy product, which I think you'll find is a little bit different than what Charles said in his talk. And then talk about how we're going to get there for our research and development path, and then just give a quick overview of our company and our present status. If you want to learn more about our company, feel free to contact me after the talk, but for this, I'm going to be primarily focusing on the technical aspects. So just as a bit of a background to talk about spheromacs and what we're doing at CT Fusion. There's this thing in fusion research called helicity injection current drive. And it's actually been used for decades, and it's been used to form spheromac configurations and sustain them, but also it's been used for non-inductive startup on spherical tokamaks, such as NSTXU at Princeton. And so magnetic helicity, which is also often denoted with the letter K, is a useful constant of motion that is conserved on timescales shorter than the resistive time. And so you can think of this quantity as the linkage of magnetic flux with magnetic flux. And we like it because it allows us to predict how magnetic equilibria will evolve during very complicated relaxation mechanisms because it is a constant of motion on a resistive timescale. You can think of this as the central solenoid of a tokamak configuration as a helicity injector, in that when you ramp the solenoid in a tokamak, you induce an electric field via Faraday's law that drives a toroidal plasma current, which is responsible for giving the colloidal magnetic field that's required for confining plasma. And so there's a method called coaxial helicity injection, or CHI, which was used to form and sustain spheromac configurations in an experiment last decade called SSPX, which was at Lawrence Livermore National Lab. And it's also used to aid in non-inductive startup on tokamaks. And so here's a picture of the SSPX experiment. So on the left here, you see a colloidal cross-section of the experiment. So it's much simpler than a tokamak in the sense that there's no central solenoid and there's no toroidal field coils. A spheromac entirely has colloidal and toroidal magnetic fields that are produced by plasma currents flowing in the plasma itself. So the way I relate this to people that research tokamaks, it's as if you took the toroidal field coils, which have currents flowing in them, and you move those currents from outside the machine to inside the machine. The interesting thing about spheromacs is that by doing that, you can have a much more compact, high power density reactor, much like some of these other approaches like field reverse configurations in the previous talk. We're all going towards these more compact, high power density, lower cost devices as a way to find a more economical fusion power product. And so spheromacs have shown great promise historically, where in this SSPX device at Lawrence Livermore, we saw maximum electron temperatures exceeding 500 eV during spheromac decay. And so we saw promising confinement quality in these devices approaching L-mode tokamak levels, if you're familiar with that. However, one issue that we observed in SSPX was that there was a significant reduction in thermal confinement during the driven phase of operation, which is synonymous with saying when we were injecting magnetic helicity into the spheromac to keep it going against resistive dissipation. The lack of good energy confinement during sustainment from SSPX kind of threw a bit of cold water on the steady-state spheromac fusion reactor concept. And so additionally, we saw relatively low current amplifications in SSPX, which related to the recirculating power fraction. Effectively, the lower that the current amplification is, the larger your power or your recirculating power fraction would be, which would ultimately reduce the power gain of your fusion power plant. And so what these results suggested that you need to have some method of spheromac sustainment that is compatible with good energy confinement and allow for high current and flux amplifications to ultimately lead to an attractive steady-state sustained spheromac fusion reactor system. And so going into those topics a little bit more in detail. So good energy confinement and high current and flux amplifications. I argue that those are the two major things that we need to show are possible simultaneously for the sustained spheromac to go down towards a fusion power plant. And so there's two things to consider. So non-axisymmetric magnetic fields are required for dynamo current drive. And so that statement in itself is distilling a really complicated topic into one sentence. But effectively, you can think of this in relation to how the sun works in generating a big magnetic fields around the sun. There is a dynamo occurring inside of the sun that gives rise to them. We're effectively using that same physical approach in our machine, but we're actually accomplishing it with an external plasma current drive system to mimic the natural processes occurring in the sun. Can we do helicity injection current drive and have it be compatible with good energy confinement? That's really what we need to show. Also, as I said, we need to get to high current amplification so that we can have really good recirculating power fractions in our eventual power plant. We need current gains of approaching 1,000 to reach an acceptable recirculating power fraction. So what are the requirements for achieving these high current or flux amplifications? So with those questions in mind, I'm going to talk about now our approach for accomplishing both of these goals simultaneously. So the helicity injected torus with steady inductive helicity injection, which we call HIT-SI, which is a lot easier than saying that mouthful, allows for the formation and sustainment of spheromac plasma configurations fully inductively. And so on the left here, you see a CAD drawing of our machine. And so effectively what we have is a bow tie copper flux conserver, which contains a toroidal magnetic configuration we call a spheromac. And you see these semi-toroidal ducts, which are our inductive helicity injectors, which form and sustain these spheromac configurations. And so typically I'm trying to explain this to tokamak researchers, and you can think of these kind of as miniature tokamaks on either side of the machine that operate in an AC fashion, but temporally out of phase with one another. And so you can think that we're injecting magnetic helicity in an AC, non-axisymmetric manner, and through natural phenomena in the plasma, that gives rise to a steady state axisymmetric spheromac toroidal object, which we use to confine plasma. And so this steady inductive helicity injection method used on HIT-SI has a few distinguishing features that may allow it for more favorable scalings towards higher performance sustained spheromacs. So one, we operate with the helicity injector lambda, which is just a measure of the curliness of the magnetic field in those injectors, higher than the curliness of the spheromac lambda. And this effectively allows for the downhill flow of magnetic helicity from the injector assemblies into the spheromac region. As I mentioned, this helicity injection is also non-axisymmetric and time-dependent. And both of these features together are required for ensuring that the spheromac remains stable during this current drive scheme. Also, since this helicity injection system is fully inductive, there's no electrodes present in the system at all. And so it actually allows for a better plasma material interaction interface by reducing the amount of plasma current exiting material surfaces, thereby injecting impurities into the plasma, which is bad for good plasma performance. But the catch with this is that we have to have an insulating plasma facing coating on our first wall to allow for this fully inductive helicity injector operation. And so on our devices, we've actually approached plasma currents of about almost up to 100 kiloamps with current gains approaching 4, which is actually a spheromac record and exceeds the performance observed on SSPX. You can see some of these plots here on the right where we're operating at higher injector frequency, where we approach those current gains of 4. And then at lower injector frequency, we reach the hundreds of kiloamp, nearly 100 kiloamp plasma currents. We believe we've seen stable sustained equilibria, ohmically heat to the Mercier beta limit, which is what we want for our confinement goal. And we hope to continue to ohmically heat all the way to our desired operating point in eventual reactor vision. Also, our surface internal and external magnetic probe measurements indicate that we do have plasma pressure confinement while operating at high frequency or when we're at the highest current gains that we observe. And you can see this via a Shafronov shift of the null of the ploidal magnetic field shifting outward at bigger major radius. So we see this as a pretty promising result. And on the pathway towards an eventual reactor with much higher current gains, we envision it to continue confining better and better as that current gain increases. The way that we understand what's going on magnetically in our device is that we actually use this process called bioorthogonal decomposition. And it gives us a measurement of exactly what the non-axisymmetric magnetic fields are doing in our devices. And we can temporally correlate those non-axisymmetric fields with either the injectors or the equilibrium or some other, for example, instability that may be emerging during operation. And what we find from this analysis is that the overwhelming majority of the non-axisymmetric magnetic activity that we observe is imposed by the helicity injectors rather than being generated by plasma instabilities. This is exactly what we want, and the fact that we're imposing what's required for dynamo current drive instead of driving the equilibrium unstable, which we think is responsible for poor energy confinement. And doing this analysis further, and from our plasma sustainment perspective, really the only thing in the system that has a sufficient amplitude magnetic perturbation to drive all of the current that we observed is the imposed magnetic perturbation. So this provides even more support that we are doing current drive, dynamo current drive via externally imposed magnetic perturbations rather than current relaxation via plasma instabilities, as was observed in SSPX previously. So this is fundamentally something new in spheromac sustainment. And so we are currently operating an upgrade of the 2-injector approach I showed you before called HIT-SI 3. And so this experiment uses the same copper flux conserver as the previous one, but instead of 2 helicity injectors, we have 3. And so you can see some pictures here of the actual machine. So there's a lot of pretty copper there in the middle picture. And on the far right there, you see a zoom in of one of the 3 helicity injectors with the wrappings on it required for performing fully inductive helicity injection. And so we find from this experiment that the spheromac formation and sustainment is very robust. Effectively, any manner that we impose these magnetic perturbations with different spectral compositions, different frequencies, and different amounts of helicity, we can robustly form and sustain spheromacs no matter what we do. And this is kind of what we expected, because really what we're doing is that we're forming the minimum energy state that a toroidal magnetic system wants to evolve to, which is a spheromac. And so this just supports that our theories are correct, and our understanding as we go forward towards a reactor are pretty well substantiated. And so here's some other cool pictures that I really like that I wanted to show you guys. And so on the 2 left photos there, we actually compute the magnetic field structure before we form the spheromac configuration at startup, and then after we form it in the middle plot there. So you see all of the red magnetic field lines wrapping around the spheromac equilibrium, which a subset of the spheromac equilibrium fields are shown in blue. And here's just a cross-section of our spheromac equilibrium, which you can see the colloidal flux surfaces draw. So that's where we're at, and that's what we're working on currently on our machine. So where do we want to go from here? So the desired point, the fusion energy products we want to make, are compact, flexible, low-cost magnetic fusion power cores producing on the order of 100 up to 1,000 plus megawatt electric net outputs. So this is much bigger than the desired output that Charles talked about in his talk. But we believe that there's going to be a pretty robust demand in the hundreds of megawatt scale, especially due to recent market trends in the US electricity market that are going towards more of the smaller power output, like natural gas plants. And we are targeting most of our products in that hundreds of megawatt range now, instead of the multi-gigawatt range, which is pretty typical for most of the fusion demo visions that you see from around the world. This patented spheromac plasma current sustainment technology is the key enabling IP, and we have an exclusive license at the company to this UW-owned IP. And it results in a 100-time improvement in the plasma sustainment of energy efficiency. And that really is what allows us to reach the very competitive recirculating power fractions, which leads to a very attractive fusion energy product at the end. We believe that this sustainment technology is the enabling technology the spheromac needs to march down towards a licensable fusion power core for electricity producing pilot plants or for high-grade processes. And so these are some of the pictures on the left that you already saw. And then on the right here is a vision for a 1 gigawatt electric power plant based on this technology, which this is just, as I said, just a vision for a single output. And we're actually targeting smaller outputs now with some miniaturized versions of this 1 gigawatt vision. But for this, we're using a molten salt or fluoride coolant, which is a 50-50 eutectic of lithium fluoride and beryllium fluoride. And we're using the single working fluid for our coolant, moderator, and tritium breeding medium. We like to use metal hydride neutron shielding to protect our equilibrium coils required for steady state operation. And so since I'm talking about neutrons, we are planning on a DT design point for our first generation power plants. And then ultimately we're pursuing, we would like to look at what a DD only reactor based on our technology would look like too. Our superconducting equilibrium coils for steady state operation need to be either low temperature superconducting or high temperature superconducting. Either one is fine. We don't need very high magnetic fields, so we don't have to use subcooled high temperature superconductors like Commonwealth is pursuing. And we're wanting to use ITER developed cryopumps for the removal of helium ash from the fusion plasma. So how are we going to get there? So this is a very stripped down version of our development path, but I think it gets the point across. And so effectively beginning in 2015 for the most recent HIT-SI3 experiment, we've been operating that and learning as much as we can using DOE funding with a little bit of funding from RPE last year. And so recently the company has secured a RPE open grant as well, which I'll talk about in detail next, which is going to help for some of our plasma driver technology demonstration and some components testing to move to basically ready ourselves for our full confinement demonstration device, where we'd like to approach kilovolt scale plasma temperatures, and that means ion and electron temperatures approaching a kilovolt. And then if all of the scaling looks good and the confinement is competitive and scales as we see fit, we'd like to pursue a pilot power plant where we're going to go for an eventual net electric demonstration. And ultimately, we'd like to see a commercial product, a licensable commercial product at some point in the 2030s. So as a brief history of our company, I just lost the, 1 second, sorry. Motion sensing light. Okay. As a brief history of our company, we started off humble beginnings in the University of Washington. We actually were given a small grant from our commercialization department called Commotion to help spin out our company. We founded CT Fusion LLC in August 2015, and then we secured our first grant as a company in June of 2018, which was a phase 1 SBIR. And we've actually are just finishing that up now, and we developed an advanced GPU-based feedback control system for controlling our helicity injector system that I showed. We recently converted to a corporation, and we secured a RPE open grant, and I'm hoping that our contract is going to be finalized very soon. And that is going to be for an amount of $3 million over a 24-month project duration. And as I mentioned, that's going to be a plasma driver technology demonstration of a lot of the critical components required for the continued development of this path to economical fusion power. So our current team at CT Fusion, so yours truly as co-founder and CEO, and then Tom Jarbo, as Matt mentioned, is the president of CT Fusion, and really has been pioneering Spheromac research for decades, and is still one of the world leaders of Spheromac development. And a lot of the technology we're commercializing at CT Fusion is from his brain. Aaron Hossack, who's also our CTO at CT Fusion, he's been working at the University of Washington for quite a while and has a lot of experience with sustained Spheromacs. And then Chris Ajimian, or is our VP of Business Development and Regulatory Affairs. He's helped us plasma physics researchers get our business details and ducks in a row. And so he's been helping a lot with getting the company ready to pursue private investment for our confinement demonstration device shortly. And so the RPE Open project is beginning imminently, which will allow for the continued development of this approach. I can give more detail as to what we're exactly doing, but I left it out for this talk. The follow-on confinement demonstration device, which we call HIT-CD for confinement demonstration. We're planning that for the near future. And this is going to provide an integrated test of sustained high temperature Spheromacs with good energy confinement. And with technical and fundraising successes, we believe we are on schedule for licensing commercial fusion power cores in the 2030s. And so with that, I'll take questions.
Congrats on the $3 million.
Yeah, thank you.
Congrats. That's big.
So the HIT-SI3 is still in the University of Washington lab, correct?
That's right, yes.
Okay.
And so as part of the RPE project, part of that $3 million is going to include a subcontract to the University of Washington, which is going to fund basically maximum performance possible on HIT-SI3. And then it's also going to fund an upgrade to that machine to create a new machine called HIT-SI-U or HIT-SI upgrade. And so we're going to be testing a new proprietary design of the helicity injector system, which should increase the efficiency further and also give us a better ability to control those magnetic perturbations we're applying on the sphere mag.
So you're a team of 4 core people, but you're using folks from the University of Washington community to assist in the work, correct?
That's right. Yeah, overall, I would say there's about 11 or 12 people working on this, directly or indirectly.
So if you were to get some sort of seed funding, about how much would you expect, and what would you do with it? What would be your initial hires, and how long would you run with it?
Well, as with most fusion R&D, it really, there's a lot to do to get to a commercial product. And so my answer to that would be dependent on the amounts we're talking about. But as far as what we need to do in the near term, I mean, as I mentioned, the RBE grant is going to be super helpful for doing a lot of components testing, which is effectively going to help us de-risk the design point of the confinement demonstration machine. But really, what we need to do is that confinement demonstration device to show if we can sustain spheromex approaching electron ion temperatures exceeding 1 kilovolt. And with that, I think we can convey to investors and our community members that we do have a promising product that I am more confident will scale towards an eventual commercial power plant.
So the timeline, the run time for the head of size, very short, milliseconds, I think I saw, or
less than 10 milliseconds. Yeah.
less than 10 milliseconds. But with the upgrade, you would aim for longer time or better confinement.
It's not so much longer time, but it's just higher performance. The reason why we have such a short pulse is because we have no active cooling on our machine. And so we can see our first wall getting a little toasty towards the end of our shot. And so ultimately, to get to longer pulses, we most need to start removing the heat load from the plasma. And so,
right.
But there's no intrinsic time limitation to how long this concept can go.
Right. I think that's important for investors to understand, is that it's relative to the plasma physics scale of things. So if the equipment can go for an hour, the plasma can go for an hour if you can prove it physically.
Yeah, there's no limitation. Like in a tokamak, for example, it's often hard to have a fully non-inductive scenario because you use the central solenoid to start up. Our method is intrinsically steady state. So we can run it as long as we like, but we run it short for obvious practical reasons.
I can keep going if nobody else. You talked about the engineering pieces of the is this still called the Dynamac? Yes?
Yeah, that's the reactor vision.
Okay.
Yeah.
So it has less coils than a tokamak, and I think you brushed over maybe that point.
Yeah, so the main, I guess the main benefit of a spheromac, much like an FRC, we're actually not two distant cousins. The only difference really is that the spheromac has finite toroidal magnetic fields, whereas most FRCs have a little bit or no toroidal magnetic fields. But we don't generate those toroidal magnetic fields with any external superconducting coils. So unlike a tokamak, we have no toroidal field coils, and we have no central solenoid. And so by removing those technological components from the reactor design, we effectively have nothing to put through our donut hole in the middle. And so by doing that, we can just shrink the entire reactor down and increase the power density of our reactor. And as Charles mentioned, size is a primary driver of cost. And so by going towards a more compact reactor vision, we reduce research and development costs and eventually the cost of our power plant. But the nice thing about a spheromac by having a toroidal magnetic field is that it can be MHD stable. There's no kinetic requirement for the configuration to be stable. Actually achieving stability in a steady state fashion while keeping it sustained, that is a consideration, and that is what we have to do, as with any other concept has to do. But the spheromac configuration by itself is stable since it has a toroidal magnetic field.
Okay.
That makes sense.
Derek, I'm interested in ash removal out of your system. Can you talk about that a little bit? Because you're talking about a steady state reactor, but it doesn't have a diverter. You're going to remove ash through the cryopumps?
Yes, that's right. So this reactor uses it's effectively a wall-supported or limited plasma. And so we're going to specifically use a relatively high edge density in order to have a good coupling to pump on with those cryopumps. But also, since we're operating at the Mercier beta limit, we're expecting that interchange instabilities, which are actually what you want for regulating the plasma pressure and getting your impurities out from the core, will maintain that operation at that beta limit. So we're actually relying on that, much like tokamaks rely on ELMs or some sort of transport to get that helium ash out of the core and into the edge so you can pump on it. And so our goal is to make sure that our helium concentration within our core confinement region is less than 3% to avoid dilution issues in the core, much like you would use in a tokamak configuration.
That,
Of using DD, catalyzed DD fuel cycle sounds quite interesting. What modifications might be needed to bring that about?
Catalyzed DD, I mean, that's a bit of, I mean, I come from my tokamak roots, that seems pretty hard to me. But DD by itself is, more challenging than DT just because of the cross sections involved, and you need to reach higher plasma temperatures than you need with DT. And so eventually, I mean, my dream is to not have to use tritium at all because it simplifies the reactor concept a lot with not having to worry about breeding tritium and making sure you extract enough to keep the closed fuel cycle going. But I'm finding that DT is pretty challenging as it is to reach 150 or 200 million degrees. So we're going to start with that, and then if that works really well, we're going to pursue advanced fuels if it makes sense to do so.
Is beta about 16%?
Yeah, the engineering beta is about 16%.
Thank you.
Peak local beta can get up to about 20 or 25%.
are there any other questions? Because I have more.
I've got another question.
All right, go ahead. What do you got?
Well, there may be a university graduate student team who would like to help work on a reactor design project. Would that be beneficial to CT Fusion?
We're certainly interested in talking. Yep, we always like university reactor visions because it seems like a lot of the reactor concepts being pursued by companies these days came out of a class. So, not that the Dynamac, that's where it started.
Okay, good. If Dr. Dolan knows of a university team, they absolutely should hook up with CT Fusion. We need all the help we can get here.
Yeah, we always like talking to universities where we have a very strong education mission.
Right. So are you looking ideally for an angel investor, a strategic partner, or like a venture capital fund? Does it matter?
So right now we're open to whoever wants to speak with us. As far as the specifics of fundraising, if you have an interest in speaking more, please feel free to reach out to me. And I'd be happy to tell you a bit more about what we're planning on doing at CT Fusion.
Okay. All right. Are there any other questions? If not, I'm good.
Yeah. How, I know this is just like kind of a crazy question almost, but when people ask, like how close are you or how much will it cost until you can sell me, a 100 megawatt device, how do you respond to that? What do you say?
Well, I think the question, the way I look at it is that multifaceted in the sense that there's R&D cost and then there's the cost of the power plant that you're pursuing, right? Both of those are hurdles. You're going to encounter the hurdles of raising the money for the R&D prior to raising the money to build your first power plant. But I think you need to make a compelling case as to what the investors are getting for their investment. And I think really what it comes down to is you have to have compelling milestones and to basically say that, you know, if you invest this, I'm not going to give you a maybe answer. I'm going to give you a yes, it works, or no, it doesn't answer. You know, as a scientist, I know that often it's very hard to get yes or no, especially in fusion. But that's why we structure our development path to effectively try to get those hard answers as soon as we can for the least amount of money we can to be efficient. Because if it turns out that the concept doesn't work, I don't think anyone should spend their money on continuing to develop it. You know, that just means it sends a signal to investors that they should put their money elsewhere. And so at CT Fusion, our perspective is we want to respect any investors that wish to invest in us and provide them full disclosure as to what they're going to get for their money and what we think has the best shot at working as far as how much money we need to fund a particular development step in our path. If that answers your question.
Yeah, no, that's a great answer. Thank you. Thank you.
Derek, with the NRC being as stringent as they are around the use of tritium and recovery of tritium, et cetera, have you actually started talking with them, looking at the costs and processes of introducing tritium to your technology?
We have not talked directly with the NRC yet, but we have talked to many experts around the US and actually in France as well, since they've been busy licensing the ITER project for tritium operations, you know, in the future. Just kind of understanding exactly what are the complexities of dealing with tritium and what's the different regulatory environments you could expect, which are dependent on how much tritium you have on site at any time.
Yeah.
So we know what that landscape looks like, and we've strategically integrated that feedback into how we've structured our development path. But overall, I don't think that we have any showstoppers as far as regulatory environment goes at this time. And I know right now, I think there's quite a bit of activity in the NRC developing a regulatory framework for fusion. And I know those activities are underway, and I'm sure we'll get some guidance in the near future about exactly what they're thinking as far as how fusion will be regulated.
So I can jump in here. At the Laser Lab at the University of Rochester, it took like maybe 15 to 20 professional engineers 4 to 5 years to build a tritium handling system. So at a cost of roughly 10 million a year over 4 years. And they had to get it certified by the NRC, the EPA, and a number of other regulatory institutions. They had air monitors that would monitor for tritium releases, and then they had a tritium reclamation system. So if it got in the air, they would capture it back. And so 4 years and maybe 20 guys' efforts. That's about how much it cost.
Yeah, that's the story I'd heard.
Which is not, it's not crazy amounts of money, but I mean, you have to have people that know what they're doing, and you got to follow through the legal parts of it. That's why tritium is, you know, it's an add-on for most people. Most teams want to do deuterium first, and then that's it. Anyway, I'm done with anything I had to say. Any more questions?
I have one question. You mentioned the use of FLIBE, molten salt wall, and kind of related to the tritium question, you can use that kind of as a marketing benefit for the destruction of long-lived fission products and you know, minor actinides. Have you thought about pitching it that way?
I've actually done a design of a fission fusion hybrid using this technology. I did not publish it, but I just wanted to see if it would work. I mean, from a neutronic standpoint, it looks good, and you can use a fusion power core to drive a subcritical nuclear waste assembly to get rid of all your radioactive waste, you know, cutting down.
You don't even need to break even, right?
No, well, you're going to break even anyway because you get quite a fission boost from all the